Welcome to this explainer. Look, today we're diving into a technology that is just so profoundly powerful, it honestly borders on magic. We're talking about quantum computing, and we're going to explore exactly how it exploits the downright bizarre rules of physics to solve problems that would literally take our normal computers the entire lifetime of the universe to figure out. Now, we need to get one thing straight right out of the gate, because it's probably the most common misconception out there. Quantum computers don't just compute faster, they compute fundamentally differently. So we're not just talking about a faster Mac or a beefed up PC here. We're talking about an entirely alien way of processing information. Here's our roadmap for today. 1. Not just faster computers. 2. The weird rules of quantum. 3. The fragility of qubits. 4. Hype versus reality today. And 5. The quantum future. All right, let's dive right into section 1, not just faster computers. We really have to begin with the foundational building blocks that separate classical machines from quantum ones. Your phone or your current laptop uses classical bits. You can think of them like microscopic switches that are strictly either a 0 or a 1. It's binary. But quantum computing uses what we call qubits. And a qubit exists in a superposition of states. That means it actually holds probabilities of being 0 and 1 simultaneously. It just kind of hangs out in this fluid, probabilistic state until you actually measure it, at which point, boom, it instantly collapses into a single definite value. Moving on to section 2, the weird rules of quantum. So to understand the actual mechanics here, let's peel back the onion on superposition and clear up a huge misconception. Superposition doesn't mean the qubit is simply both 0 and 1 at the exact same time. That's kind of misleading. Actually, scratch that. It's very misleading. Rather, the qubit has a probability of being 0 and a probability of being 1. And those probabilities are what actually encode the information. By using operations like the Hadamard gate, scientists can create this state to really carefully manipulate those probability amplitudes. And honestly, the scale of what we're dealing with here is just staggering. It's called quantum parallelism. Check this out. A basic 3-qubit system can represent 8 states simultaneously. But if you have a 300-qubit system, that represents 2 to the power of 300 states all at once. To put that completely wild number into perspective for you, that is actually more simultaneous states than there are atoms in the observable universe. It's mind-blowing. And quantum algorithms can manipulate all of these states simultaneously. But wait, it gets weirder. Then we add entanglement to the mix. This is when 2 qubits become linked in such a way that measuring one instantly determines the state of the other. So if one qubit flips here on Earth, its entangled partner could hypothetically be sitting on Mars and flip instantly, completely ignoring the physical distance between them. In these quantum machines, gates like the CNOT gate are used to create this profound link, and it serves as a massive resource for quantum computation. Now, if you're feeling a bit confused or overwhelmed right now, don't worry, you are in the best possible company. Even Albert Einstein found entanglement deeply weird and unsettling. He famously called it spooky action at a distance. It totally defies our everyday logic. So, if this is giving you a bit of a headache, congratulations, you're officially on the exact same level as a Nobel laureate. So, with all these infinite possibilities and spooky links, how do we actually get a useful answer out of the machine? Well, the secret ingredient is interference. Think of it just like physical ripples in a pond crashing into each other. Quantum algorithms use wave-like interference to amplify the probability amplitudes for the correct answers while perfectly canceling out the wrong ones. That's the actual mechanism these algorithms use to pull a single, useful result out of the utter chaos of superposition. Okay, hearing all about this immense, mind-bending theoretical power, you're probably asking yourself the obvious question. So, where is my quantum laptop? It's exactly what I'd be asking. And that perfectly pivots us from the theoretical magic of quantum physics to our very real, current physical limitations. Which brings us to section 3, the fragility of qubits. Here's the big catch, and frankly, it's one of the greatest engineering hurdles in human history. The fundamental challenge is called decoherence. You see, qubits are incredibly fragile. Absolutely any interaction with the outside environment completely ruins the computation. If there's a tiny vibration, a minuscule amount of heat, or even stray electromagnetic noise, it causes decoherence, which instantly destroys that delicate superposition. This is exactly why these systems have to be cooled down to near absolute zero, which is literally colder than the vacuum of deep space. So, to overcome this decoherence, scientists are developing something called quantum error correction. Because the hardware is so incredibly fragile, you can't just use one physical qubit. First, you have to gather around 1,000 noisy physical qubits. Next, you apply surface codes to create massive mathematical redundancy. And finally, all those physical qubits work together to form just one single, reliable, fault-tolerant, logical qubit. Just imagine needing 1,000 steering wheels just to keep one single car driving straight. That's the massive hardware overhead we're dealing with just to do reliable math.
All right, let's move to section 4, hype versus reality today.
Grounding this explainer right now in the year 2026, the reality is that the most advanced systems from major players, companies like IBM, Google, IonQ, and Quantitanium, they do have hundreds or even thousands of physical qubits, but the vast majority are still quite error-prone. That being said, earth-shattering milestones are already happening. Let's talk about quantum advantage. Back in 2019, Google claimed a massive victory with their 53-qubit Sycamore processor. It actually completed a highly specific mathematical task in just 200 seconds. Google calculated that that exact same task would take the world's absolute best classical supercomputer 10,000 years to finish. 10,000 years versus 200 seconds. Let that sink in. Now, as this industry continues to grow, you're going to see two main types of machines. On one side, we have gate-based quantum computers, which are championed by folks like IBM and Google. These are theoretically universal, meaning one day they could potentially run any algorithm. On the other side, we have quantum annealers made by companies like D-Wave. These are highly specialized machines designed strictly for specific optimization problems. They're basically purpose-built. Let's take a second to just cut through the mainstream media noise. Look at what quantum computers are not. They are not simply faster classical computers. They are not replacements for your laptop or your smartphone. And they're definitely not general-purpose tools. You are not going to be using a quantum chandelier to play Doom or, browse TikTok. They are highly specialized instruments designed strictly for very specific problem types. And that leads us to Section 5, the quantum future. When these tools are finally scaled up and error-corrected, there are two massive algorithms you really need to know about. First up is Grover's algorithm. This one searches unsorted databases and offers a universal quadratic speedup. Super useful, right? But then we have Shor's algorithm. Shor's offers an exponential speedup for factoring large numbers. And why does that matter? Well, because factoring large numbers is the very foundation of RSA encryption. If a quantum computer runs Shor's algorithm at scale, it essentially breaks global internet encryption as we know it. This is exactly why governments are panicking right now, and NIST is rushing to standardize post-quantum cryptography as we speak.
So, the big question, when is all this actually happening? Well, here's a realistic timeline. In the near term, so around 5 years out, we can expect breakthroughs in quantum simulation for drug discovery and material science. Basically, simulating molecular behaviors that classical computers literally can't do accurately. Medium term, in about 10 years or so, we'll likely see massive quantum optimization for global logistics and supply chains. And long term, looking 15+ years out, that's when we enter the era of cryptographically relevant computing, where breaking encryption actually becomes a reality.
Which leaves us with this final provocative thought. Will you be ready when quantum computing completely rewrites the rules of encryption, medicine, and AI? Because make no mistake, this technological revolution is going to happen within your lifetime. And now you finally understand what it actually is. Thank you so much for joining me for this explainer. Stay curious, and I'll see you next time.